Hello. Okay. Yeah, I'll start sharing my screen. So today we continue going through some of the problems from assignment 5. So I believe the deadline is the 5th of February. So you got one more week. You got one more week to do it. And so let's get to it. So we're talking about physics today again. I had a shout out in Slack which problems you'd like to go through, but I received no answer today. If you have any particular problems you'd like to go through, do let me know. Happy to do that. So the problems are reasonably straightforward. I tried to pick the unusual ones, so 3. So let's see. Comment on the following, giving necessary corrections. So this is quite an unusual task, but if you're familiar with circuits and uncertainties, you'll be fairly confident with this. So the voltage and current across the resistor. So it says here that the voltage is 78.46. Now, if there's no other information given, we have to assume that this is 78.46 plus or minus 0.01 volts. And if it's 13.56, it's 13.56 plus or minus 0.01 milliamps. Now, alternatively, or you could say that it is 78.46 plus or minus 0.005 volts, 13.56 plus or minus 0.005 milliamps. Now, but I find both are correct. Yes, both are valid methods. I always tend to be extra cautious, and I go for the bigger uncertainty. I go for this. I choose this over this. Because this is a bit clunky, because you kind of have to add another significant figure, which is, well, hard to justify in a way. So why? Well, you have 13.56, and now it becomes 13.560, because you have to the uncertainty. Well, at least according to the A-level practice, the number has to match the decimal place in the value has to match the number of decimal places in the uncertainty. So writing 13.56 plus or minus 0.005 would be a mistake, at least if you're doing science, if you're doing experiments, that's okay. But in A levels, they really don't like it. They will mark you down for that. So I would always choose this uncertainty, because this way you have a slightly bigger uncertainty, and well, you have a better chance of your value getting into the uncertainty. So it just makes life a little bit easier. Anyways, so what is the power? So one student says it's 1.1, and the other student says it's 1063.9. Probably both of them are wrong, let's try to figure out why. So the percentage uncertainty, you need the percentage uncertainty in the voltage is 0.01. 0.01 divided by 78.46. Yeah. Let's see. Well, that's what we're trying to figure out, whether they are they're both correct. So the percentage uncertainty for voltage is 0.01 divided by 78.46, which is 0.013%. And the percentage uncertainty for current is 0.01 divided by 13.56. 13.56. It's 0.074%. Okay. And we need to add the percentage uncertainties. So the percentage uncertainty for power, well, the power is current times voltage. So it's 13.56 milliamps times voltage, which is 78.46 volts. So 13.56 times 78.46, 1063.9176 watts. So the percentage uncertainty for power is zero. Well, let's do it properly. It's the percentage uncertainty for current plus the percentage uncertainty for voltage, which is 0.074 plus 0.013, which is 0.087%. And then you take 0.087% of the power. So the uncertainty, this is the percentage uncertainty for power. So the uncertainty for power, the absolute uncertainty, is 0.087% multiplied by 10639176 times 0.00087. You get 0.93 watts. So the power is 1063.9176 plus or minus 0.93 watts. And now we apply the rules. So I prefer to write it down like this and then say, well, look, the uncertainty has to be one significant figure. So we cross out the 3. And then the value has to be rounded to the same decimal places. So we cross out this. So the answer is 1063.9 plus or minus 0.9. So I would say the second student is correct. Well, is more correct than, oh, that's milliwatts, of course. That's milliwatts. Milliwatts. Now 1.1 is too rough because you have much more precise data than 1.1. If that makes sense. Okay. So for the first student, well, .064. Yeah, I mean, if you were doing an experiment, this would be your answer. So the second student is close. Anyways, B, the dimensions of a rectangular block. So that's B. A. So this is question A. This is question B. Dimension rectangular block measured 52.2, so 35.5. It has a density of the recorded volume and mass are this. Okay. Well, there are too many significant figures. Obviously, you can see that. I don't know about the mass. The mass, I guess the mass is calculated. So we have to assume that this is a calculated value and this is a calculated value. So therefore, you have the volume. Volume is width times length times height, which is 52.5 times 35.5 times 95.0. But these are in millimeters. So times 10 to the minus 9. Well, it's 1.7705625 times 10 to the minus 4 cubic meters. And the uncertainty, so the percentage uncertainty for volume is the percentage uncertainty for length plus the percentage uncertainty for width plus the percentage uncertainty for height. And we're not given the percentage uncertainties, so we have to assume that it is 0.1. 0.1 divided by 52.5 plus 0.1 divided by 35.5 plus 0.1 divided by 95.0. So this is uncertainty to the best of our knowledge, and this is a common practice as well. 52.5. If you're not given the uncertainties, 0.1 divided by 35.5. If you're not given the absolute uncertainties, divided by 95.0. So this is 0.5758%. 0.58%. So the volume, as a matter of fact, so 0.58% times 1.7705 times 10 to the minus 4. It's 1.7705 times 10 to the minus 4 plus or minus 1.022 times 10 to the minus 6. Now this looks a little horrible, so we have to do this 177.05 times 10 to the minus 6. Well, like this, plus or minus 1.022 times 10 to the minus 6 cubic meters. So it's 177 plus or minus 1 times 10 to the minus 6 meters cubed. So the answer would be not this. You have too many significant figures, is 177. Okay, too many sig fig. This would be 0.000177 cubic meters. Well, plus or minus 0.0000001. Okay, cubic meters. And the mass, well, we need the percentage uncertainty. We need the percentage uncertainty for the density. And this is going to be huge. So it's 0.1 divided by 4.3. So 0.1 divided by 4.3, which is 2.3%. 2.3%. So the uncertainty in mass, the percentage uncertainty in mass is 2.3% plus 0.58%, 2 plus 0.0058. So that's 2.91%. And so the mass is density times volume. So it's 4.3 times 10 to the 3 multiplied by the volume, which is 177 times 10 to the minus 6. So 4.3 times 177. So 761.1 times 10 to the minus 3, which is 0.7611 kilograms. Now the uncertainty is 220. So the uncertainty in mass is 2.91% times the mass, 0.7611, equals times 0.00291. It's 2 kilograms. That doesn't make any sense. Two grams, I think. Oh yes, divided by 1,000. And so the uncertainty is 0.002 kilograms. So the mass must be 0.761 plus or minus 0.002 kilograms. Okay, this is the correct This is the correct value. Okay, I'm not going to do C unless you'd like me to. The idea is the same. So you just look at the uncertainties. But I'd say this is a problem about uncertainties. Okay. Now this one doesn't make any sense whatsoever. In C, the current cannot be 0, is 8.03 because the batteries are in reverse. So the combined EMF is 0.1 volt and the combined resistance is 3 ohms. So the current will be 0.1 divided by 3, which is going to be 0.033 amps. So it cannot be 8.03. 8.3 amps. And then you do the uncertainties. Okay, moving on to the next question. Problem 4. Positive charges of equal magnitude Q are located at 3 corners of a square. Okay. This looks familiar. So Q, Q, Q. So plus Q, plus Q, plus Q, and the side length of A. What is the electrical potential and the electrical field strength at the 4th corner? So we need to find the field, and we need to find the potential. Potential is, well, it's usually V. Okay. So the field from a point charge. Field from a point charge. Charge is 1/4 pi epsilon 0 multiplied by Q over R squared. Okay, so we have at this point we have 3 fields. So let's label this point I don't know, A. So at A, there are 3 fields. One's going like this, one's going like this, and another one's going like this. Please tell me where I made a mistake in this diagram. E1, E2, E3. It's a subtle mistake, but it is a mistake. So I'm standing at point A and being pushed by 3 electric fields in 3 directions. Where's the mistake in my diagram? So Hannah, yes, you've noticed that the magnitude is different. Good. Are they equal magnitude? Sure, should they be equal magnitude? No. Why are the 3 fields not of equal magnitude? Are the 3 charges equally separated from point A? Can you use your mic?
No.
Sorry?
No.
Yeah, they're not separated. The third one, so B, C, and D. C is located further away. So if this is A, but this is square root 2A. Root 2A. So this field, the mistake is that this field has to be weaker, like this. This would be the correct diagram. Okay. So these are stronger fields. This is a weaker field. Anyways, E1 is Q over 4 pi epsilon 0 A squared. E3 is the same thing, Q over 4 pi epsilon 0 A squared. And E2 is Q 4 pi epsilon 0 2A squared. Okay, and now you add the E1 and E3. So E1 plus E3 as vectors is going to be a vector, well, the modulus of E1 plus E3, of course. And this will be square root of 2 times E1. Well, quite obviously, E3 and E1 exert a force in E2. No, they don't. There are 3 independent fields. You're using the principal superposition to add them. You're sending direct messages. It's better if you send it to the chat, so everyone can see what you're saying. Okay, so square root of 2E1. Well, modulus of E1. So it's square root of 2 Q over 4 pi epsilon 0 A squared. And then the total field is going to be, because E1 plus E3 adds up to vector like this. So E1 plus E3, it's a vector in the same direction as E2. You can simply say that's E2 plus this square root of 2Q 4 pi epsilon 0 A squared, which is 2 so Q 1 plus 2 square roots of 2 over 4 pi epsilon 0 A squared and a 2, so 8, like this. This is the final answer. Okay. Any questions? No questions? Okay. So this is important to understand, that this is a vector, of course, at 45 degrees. So direction 45 degrees to vertical, or simply southwest direction. Now the potential. Now potential is a scalar. So potential from a point charge. It's 1/4πε0 multiplied by Q over R with no square. And potential is a scalar, so the total potential is equal to V1 plus V2 plus V3. So it's Q divided by 4πε0 multiplied, open brackets, so 1/R plus 1/√2R plus 1/R. And then you just do, so square root of 2, square root of 2, 2 square root of 2. So Q multiplied by 1 plus 2 square roots of 2 over 4 square roots of 2 πε0 R. I think so. I think I haven't made, I think I haven't messed it up. Questions? How well, on a scale of 1 to 10, do you understand this answer? The first one, this one, on a scale of 1 to 10. Ten being I understand fully. And the rest. What's going on? So Kieran, Matty, Ethan. Matthew, thank you. Ethan. Ah, didn't know the question. Okay, that's fine. And how well do you understand the potential? The answer for the potential on a scale of 1 to 10. Okay. And the rest, I assume, tens. If the okay, is there something in particular you don't understand, Hannah, or is it the maths bit or the physics bit that you are unsure about? Okay. No answer. Anyways, how much time do we have? Oh, we just barely started. Okay, that's good to know. Let me just skim through what I've prepared for you today. Okay. The ends of a uniform Y cross-sectional area 1 times 10 to the minus 6 meters squared, and negligible mass are attached to fixed points A and B, which are 1 meter apart. So diagram A and B. The wire is initially straight and unstretched. A mass of 0.5 kilograms is attached to the midpoint of the wire. 0.5 kilograms. Are attached to the midpoint of the wire hanging when the midpoint is at a distance 10 millimeters below the line AB. Calculate the Young's modulus for the wire. Okay, so the shorter questions tend to be harder. I don't know if you noticed. Well, what's going on here? So the wire is horizontal. You attach a mass and the wire becomes non-horizontal. So I would draw another diagram. Say, okay. So this, and like this. So exaggerated perhaps because it's only 10 millimeters. 10 millimeters. 10 millimeters. Now, before we start doing this question, can you tell me why a wire hanging horizontally is something absolutely impossible? A horizontal wire. Impossible. Why? Well, actually, it is impossible. Impossible. Why is a horizontal wire impossible? Have you ever seen wires? How do they look like? Like high voltage cables, for example.
Is it because the wire has a mass, so the only force downwards is the mass, so it has to go down?
Yeah, absolutely. So if you take the middle of the wire, there is tension in the wire. So let's say the wire is horizontal. There's tension in the wire left and right. But then there is the weight of the wire, which is mg, which is pulls down, and it's not compensated by any other force. So until the tension is, if the tension in the wire is horizontal, there's no vertical component. So the wire will always slack. The wire will always slack, even a tiny bit, but it will slack. Now here we're using, it's a negligible mass. So it's a very, very light wire. So the slack is very, very, very small, and therefore we can ignore it. But overall, horizontal wires are not possible. Okay. Does everyone understand this? Put a 1 or a 0. Do you understand why a horizontal wire? Oh, okay, Hannah, you increase the horizontal tension. So you increase it. But this force is still unbalanced. This force, even if it's a very, very small force, it's still unbalanced. That's because the horizontal tension forces have no horizontal or vertical components. Yeah, are you on board now? Got it. Good. Anyways, we can ignore that because the wire isn't horizontal anymore because we've added some mass. So there's a force here, which is mg. And there are two tension forces, T and T. T and T. Right. And we can assume that this angle is theta. Okay. So we need the forces in the x direction and in the y direction. The x direction in the y direction. So, well, let's do it properly. Newton's second law. Mass acceleration in the x direction is equal to t cos theta minus t cos theta, and that's equal to 0. Well, yeah, that's obvious because this is t cos theta, and this is t cos theta. So horizontally, it is not moving. Duh, but I mean, just, yeah, I'd practice using Newton's second law. So mass acceleration in the y direction is equal to the upwards forces minus the downwards forces. So t sine theta plus t sine theta minus mg. And that also equals to 0 because it's not moving, it's not accelerating. So yeah. So basically we have two equations. Well, we don't need the first one. Realistically, we only need the second. So 2t sine theta equals mg. And what are we looking for? T. Oh, we need the Young's modulus. Well, to find the Young's modulus, we need T, of course. T is equal to mg divided by 2 sine theta. Okay. And we know that the Young's modulus, E, is equal to stress over strain. And we know that stress is tension divided by cross-sectional area, and strain is the extension divided by original length. Cross-sectional area. So we know the tension, we know the cross-sectional, we know the cross-sectional area, we need the extension. Well, the extension, delta L, the extra length, is going to be, well, it's the difference between the new length and the old length. So it's the hypotenuse minus, so it's going to be, let's say the original length is L. The original length is L. So it's going to be square root of L over 2 squared plus, well, let's call this what, delta y plus delta y squared, delta L squared plus delta y squared. This is, I'm using Pythagoras theorem here, delta L, and it's double that. Minus L. Gosh. That's horrible. It looks horrible. It's not. Okay, let's do it properly. Confused.com. So we have the slack. The slack is delta y. This is the original length, L over 2. That's half. We're looking at this triangle. This angle is theta, and this is L over 2. Oh, well, we need to find this angle. Oh, we don't really need we don't need Pythagoras. Sorry, it's much easier. So this side is going to be L over 2 divided by cos theta. So L over 2 cos theta. All right, so we have L over 2 cos theta multiplied by 2 minus L over 2 times 2. Well, actually, this is the extension, so twice that. The extension is the difference between the hypotenuse and the adjacent side. And we double that because we have a symmetrical on the other side. So we have L over cos theta minus L, which is L 1 over cos theta minus 1. Okay, which is nice. That's the extension, original length. So the strain on the wire is delta L divided by L, which is 1 over cos theta minus 1, which is 1 minus cos theta over cos theta. And stress is that. Okay, that's fine. So Young's modulus is the tension, which is mg divided by 2 sine theta multiplied by A multiplied by 1 minus cos theta over cos theta. And this is tan. Sine over cos is tan. So it's mg 2 tan theta area multiplied by 1 minus cos theta. 1 minus cos theta. Oh, that's not going to be nice, but anyways, we know that the tangent theta is equal to delta y over delta y over L over 2. So 2 delta y over L over 2 A. 1 minus cos theta is L over 2 over L over 2 squared plus delta y squared. Okay, and then mg. Then you just substitute and you get the value. Okay. Notice how I didn't put any numbers until the very last moment. And I prefer to do it this way. This helps you to make sure you're not making mistakes. So for example, L over 2 is measured in meters. So I apply dimension analysis here. So what I do is I check myself, have I messed up or not? Which I can easily do. I very often do that, but I can double check myself. Look, this is meters, and this is meters squared by square root, so that's also meters. So meters and meters cancel out. So this is a dimensionless number, which is valid because 1 minus a dimensionless number is fine. Then we have delta y, that's meters. A is meter, L is meters as well, so that cancels out. So we have newtons divided by square meters. Is that what we are expecting? Well, yes, because the Young's modulus is measured in pascals, which is true because this is newtons and this is square meters. So at least unit-wise, I haven't messed it up. Okay, there are many other ways how I can mess it up, but it looks like the answer does make sense. Okay. You can also well, anyways. You can also double check yourself, like what happens if delta y increases? If delta y increases, the Young's modulus decreases. Does that make sense? Well, yes, if you have a stiffer wire, the displacement will be less. Makes perfect sense. A stiffer wire will lead to less downwards displacement. So this is how you can check your answer, like it's a sanity check. Okay. I don't want to put this in a calculator. I'm sure you can do it by yourself. Yeah, so everything is given to you. Okay. I hope that's fine. I've already spent 15 minutes on this, so I don't want to go any further. Good. An experiment to the photoelectric effect. We might just skip this one. Oh, I like this one. Let's do this one. GPS satellites. GPS satellites, navigation. One GPS satellite is in a circular orbit at a height h above the surface of the Earth. The Earth has a mass m and radius r. Show that the angular speed of the satellite. So we have the planet Earth. Now the satellites go around the Earth at quite a large altitude. Okay, which is roughly, I think it's 20,000 kilometers-ish. Because if you look at the International Space Station, which you can very often see in the sky, who has seen the International Space Station in the sky? Just when you look up and you see it. Anyone? Say put a 1 or 0. Anyone? Can people hear me? You haven't seen, okay? Just one person, right? No. So how to see it? Early evening. So when the sky is clear and the sun has set, you can see it for about an hour or two after sunset. What it looks like a very bright star, like the brightest star, and which travels across the sky quite fast. So it crosses the sky in about 3-4 minutes. It crosses the whole sky. It goes from one place to the other. Sometimes it disappears because it goes into the shadow of the Earth. But it is a very nice thing to see. Now it goes around the Earth every hour and a half. Therefore, you can very often see it. It's easy to mistake for an airplane, but airplanes flash, and this one doesn't flash. It's just a bright star. And there's a website called Track the ISS. It's not called Track the ISS, but it's called something like that. You can search it, and which tells you in real time where the space station is. But in the summer, one summer, I think it's 2020, I just saw it almost every day. And I was like, I wonder if the space station is up there. And you look up and, oh, it's there. But it appears every hour and a half, as I said. And okay. You won't see it every hour and a half, but yes, it goes around the Earth every hour and a half, and sometimes you can see it. Okay, so if you were to draw the International Space Station, this is only 400 kilometers above the ground. So it's going to be like this. So the space station is like this. but the other satellites are much further away. Oh, sorry, that's not GPS, that's geostationary. I've confused the two. But anyways, a satellite. So we have the radius of the Earth. We have the height above the Earth. And we have a satellite here performing circular motion. So it's traveling at, well, we know that there's only one force, which is mg. And oh no, sorry, don't do that. It's the force, it's the gravitational force. And the gravitational force is equal to mass of the satellite, mass of the planet, gravitational constant, divided by r plus h squared. Now, we know that this force is the centripetal force. So ma equals Fg, but we know that A is the centripetal force, so m omega squared r, which is the radius of the orbit, so r plus h, is equal to g m over r plus h squared, and m cancels. You got r plus h, so omega squared is g m r plus h cubed. So omega is square root of gm over r plus h cubed. Quite a fun task. Really enjoyed that. Any questions? So this is Newton's second law. Second law. Any questions? Yes, no, maybe? Okay. B, calculate the orbital period of the satellite when h equals 2.02 times 10 to the 7. Orbital period when h is this. Well, I assume you need to look up the values of so you need. I assume that you know the mass of the planet. Yeah, so the orbital period is 2 pi divided by omega. Yep. So it's 2 pi divided by well, square root of gm r plus h cubed, and yeah, you get a value. Well, the radius of the Earth is 6,400 kilometers, so it's 2 pi multiplied by 6,400 plus h. Well, that's times 10 to the 3 plus h, which is 2.02 times 10 to the 7 square cubed divided by gm, so 6.67 times 10 to the minus 11 times the mass of the Earth. Mass of the Earth, I believe, is 6 times 10 to the 24. Mass. Yeah, 6 times 10 to the 24. 6 times 10 to the 24 kilograms. And you get a number. You get a number which I assume is going to be very close to 24 hours. But let's check. So 2 pi times square root of 6,400,000 plus 2.02 times 10 to the 7. That's cubed divided by 6.67 times 10 to the minus 11 multiplied by 6 times 10 to the 24. Oh no, so it's 43,088 seconds divided by 60 divided by 60, which is 11.96 hours. Okay. Figure below that shows the orbital plane of the satellite inclined at an angle to the equator. X, Y, Z are locations on the Earth. X is the North Pole, Y is on a high mountain, and Z is on the equator. The satellite is to be launched from one of these locations. State and explain which launch site minimizes the amount of fuel required to send the satellite into orbit. North Pole. Y is on a high mountain and Z is on the equator. Well, I'm gonna go with the equator. Like high mountain, like what is a high mountain? It's like, it's not Mount Everest, certainly. You can save some energy if you are launching from the top of Mount Everest, because you, first of all, you spend less energy on fighting against air resistance, of course, because the air is much thinner. Secondly, you are already high above the ground. It's 8 kilometers, but satellites are 20,000 kilometers. So, like, 8,000 kilometers doesn't really make a difference if you think about it. The biggest thing, so on the pole X, there's no benefits. On Y, there is less fuel because the satellite already has GPE. So less fuel. Also, it has some speed, some kinetic energy due to the rotation of the Earth, because rotation of Earth. And finally, less air resistance. The first one is negligible because the satellite's it's 20,000 kilometers and the highest mountain is only 8 kilometers. Okay, 8.8 kilometers to be precise. 8.848 to be even more precise. So that doesn't really help you. You have some kinetic energy because the Earth is rotating, true. And it's less air resistance as you break through the atmosphere. It's not that significant because when you're close to when the rocket launches, you start with low speed and you only gain speed as you go higher and higher. So by the time the rocket travels really fast, it is already above the level of highest mountain. So the only first, like, I don't know, 10, 15, 20 seconds when you're breaking the first 8 kilometers of the toughest atmosphere. So the biggest thing would be the kinetic energy due to the rotation of the Earth. And if you're at the equator, the satellite is already traveling faster. So here, the satellite is traveling like this, like even before launching, even before firing up the rocket, the satellite, which is on the equator, already is traveling at 500 meters per second. And satellites travel at about 7,000 meters per second. So you already have a big chunk of energy. So you need less fuel. So that's why, if you look at the States, there are 2 launch pads in the United States. One is in Florida, one is in California. So they're both located as close to the equator as possible. The main launch sites, for example, in the USSR, they had the launch site in Kazakhstan, which, it's still there. It's the launch site is in Kazakhstan, so it's really, really far south. So as far south as you can go. That was always the aim of any space launch. Okay. Then the satellite has a mass of 1630 calculated gravitational potential energy when it is in the orbit. So gravitational potential energy. So that's D. So C, Z as kinetic energy due to rotation of planet, and D gravitational potential energy. So GPE is equal to so it's minus G M over R plus H. Yeah, this is the formula, and I'm sure you can calculate it. It's going to be negative. How would you understand that the gravitational potential energy of a satellite is negative? It's way up above the ground. So how come it is negative?
Because it's almost like you require negative energy to get to the Earth. It attracts you to the Earth.
So what's your energy on the surface of the Earth?
I mean, you still have some, don't you?
Do you have more or less?
Less negative.
So closer to 0.
Yeah.
No, that's incorrect.
Oh,
The
sorry. More negative because R is smaller.
Yeah, R is smaller, so of course, if you look at the formula, so the gravitational energy is like this. So this is R, well, R, small r, and this is GPE. So the surface of the Earth, it's going to be something like this. Well, inside the Earth, of course, it's going to be different. So like this. Inside the Earth, it's going to go like this, but that's not that important. So yeah, it becomes less negative. At infinity, our GPE is 0. At infinity, GPE is 0. And here it is negative. Now, what does that mean? Well, you need energy to remove the satellite from the gravitational field of the Earth. So if you take a satellite, you give it a massive rocket with, I don't know, 7 billion joules of energy, and you give it all that energy, and that's enough to remove the satellite far away from the planet, and then it will stop. And the total energy will be 0. Okay, so at infinity, the energy is 0, and you need energy to get to infinity. Therefore, your energy has to be negative. You have negative energy plus kinetic energy. Like to go into infinity, you need you need positive energy to get to infinity. Therefore, your current energy is 0. I hope that makes sense. So I'm sure you can calculate that. This is just a calculator exercise. So let's talk about E. A different satellite is in a higher circular orbit. Explain how the linear speed of the satellite compares to the linear speed of the satellite in part A. It's going to be slower. It's going to be slower. So how come it's going to be slower? Because the gravitational force is m over r plus h squared g. It's equal to mv squared over r plus h because it's circular motion. So this cancels, m cancels, and you can see that v squared is equal to gm over r plus h. Therefore, if h is bigger, if h is greater than v, v is smaller. Yes, if h increases, v decreases. Okay. How much time do we have? Oh, these are lovely questions. But let's do this one. This is a thermodynamics question. A number of assumptions are made when explaining the behavior of a gas using the molecular kinetic energy theory. State these assumptions. Well, you should know these pretty well. Have you done molecular kinetic theory? It's at school. Yes or no? Okay. So you should know them. They that the molecules are far apart. The time of the collisions is negligible compared to the time between collisions. The collisions are perfectly elastic. The what else? Molecules have only kinetic energy. There's no potential energy. Therefore, they cannot stick together. There are no intermolecular forces except in collisions. The size of the molecules is negligible compared to the volume of the gas. Yeah, I think that's about it. The graph shows how the pressure changes with the volume for a fixed mass of ideal gas. So these diagrams, like at school, you're told that what you're doing is called thermodynamics. Unfortunately, it is not. Thermodynamics has to do about the energy of a gas, and you don't do that. You don't study the energy of a gas, like the work done by a gas, unless you're doing something other than A levels, which so you probably do. So, for example, if you're doing IB, or if you're doing pre-U instead of A levels, then you would be familiar with this. Is there anyone doing something else rather than A level amongst you? Do we have any non-A level students, like IB students or pre-U students? No. Okay. So thermodynamics is the study of the work done by a gas, effectively. So this is the pressure of a gas, and this is the volume of a gas. At A, the temperature of the gas is 27 degrees Celsius. The gas undergoes two changes, from A to B and from B to C. Calculate the number of gas molecules trapped in the cylinder using the information from the initial situation at A. Okay, at A. So we have PV equals NKT and RT, sorry, and RT. So N is PV divided by RT. So pressure is 1 times 10 to the 5, 1 times 10 to the 5. Volume is 10 to the minus 3. The RR is 8.31. Temperature is 300 Kelvin. Yes, 300 K. 10 to the minus 5, so 10 to the 2, 3. So it's 1 divided by 8.31 divided by 3. So that's 0.0401 moles. I believe I haven't made a mistake. Okay. So this is very straightforward. C, calculate in Kelvin the change in temperature of the gas during the compression that occurs between A and B. So we need to find the new temperature of the gas. So that is question B. This question C. So the temperature of the gas is PV divided by NR. So pressure is still the same. It's 1 times 10 to the 5. The volume has decreased. Sorry, this is 0.7. So I've made a mistake. Times 0.7. That's 0.028. 28. 0.028 moles. 0.5 times 10 to the minus 3 divided by n, which is 0.028, multiplied by r, which is 8.31, and that's 10 to the 5, 10 to the power 5, multiplied by 0.5 times 10 to the minus 3, divided by 0.028 times 8.31. That's 215. 215 Kelvin. Okay, this is something that we call isobaric compression. So AB is an isobaric compression. So we're compressing the gas at constant pressure. Okay, the temperature of the gas decreases. Okay. From B to C, so the change in temperature is of course 85 Kelvin. It was 300, now it's 215. Deduce whether the temperature of the gas changes during the compression from B to C. And the answer is yes, it does. How would you do that? How can you tell that it changes?
PV isn't constant.
PV is not constant, of course. Therefore, it is not an isothermic process. So, and then you just, yes. Compare the work done on the gas during the change from A to B with that B to C on the graph. Well, the work done on the gas is the area under the graph. So the work is pressure times delta V. And here the delta V is the same. This is the work done in the process AB. And this is the work done in the process BC. And so the work BC is greater than the work AB. All right, so that's that. We might go into magnetism next week. So the assignment is ready. It will be published next week. And yeah, so maybe instead of doing past exam questions, we'll do some magnetism. Okay. All right, so I hope that was useful, and I'll see you next week.
Thank you, sir. Goodbye.
Welcome.